thank you for this embarrassing introduction. I hope it is a great pleasure for me to be here. I was just telling Gislen and Wessam and Hafed that I was very keen to take advantage of your permission to talk about something less formal. So I decided to talk to you a little bit about my research program as it has evolved through what I think of now as great opportunities, but it sounds better if I talk about fortunate accidents. For those of you who have children and have read the Unfortunate Events series, I think that's what I'm trying to allude to. So I'll tell you about 3 projects and their background stories about how they came to happen. I think that none of them were truly planned, even though when we write our NSERC discovery proposals, we tell a story that says that we had a grand plan for the last 10 years and everything that happened is part of this grand plan. Thinking about how things really happened, we all recognize that there were some key opportunities that were never under our control. So I'll tell you a little bit about the Smart Condo project, the Vibrant Minds project, and the Smart Buildings activity that I'm currently engaged in. So these are the projects, and the top line of my outline here talks about the software engineering problem in the context of which these activities happened. So let me start a little bit about the Smart Condo project. And we're talking about the year 2010 around. I had been working on legacy systems reengineering, migration of code from one platform to the other, analysis of the design of object-oriented systems. This was my work before 2010. And because of this work, I came in close collaboration with IBM, got a bunch of Eclipse grants in the context of the work that Zhenchang Xin had done on UML-DIF. That's still the work that I am terribly proud of, analyzing object-oriented systems. And at the time I had a chair, and IBM was interested in complex software architectures. So not only the object-oriented code of a package, a system, a software system that is object-oriented, developed in Java, that had been primarily what I was doing until then, but really things that involve distributed systems, complex data, interesting uses of their databases, and at the time they were launching WebSphere sensor events. And I had colleagues that were working on sensor networks, and we came with the idea of working on a smart mousetrap. And this idea came from an institute here at the U of A, the Alberta Biodiversity Monitoring Institute. And the way they work, they send graduate students every spring to put traps out there in the forest to collect different animals and weigh them a couple of months later to see how animals forage and how they eat and what's their weight and how they survive. So we thought that we would make the work simpler for graduate students if we had these smart mousetraps that would have cameras and weight scales to measure the animals. And that was what we were talking about. And then suddenly I met Lily Liu. She's a professor in occupational therapy, and she had a collaboration with the Glenrose Rehabilitation Hospital. And she said, you know what? The Glenrose has a room, they call it the rehabilitation suite. And what they want to do there is they want to observe patients after they had major surgery before they go home, because they do not want to send people home if they don't feel comfortable that the people are able to take care of themselves. So they really need to observe people without actually helping them. Well, you know, we were about to build the mousetrap thing. We in fact had the mousetrap. We built the mousetrap in the lab. But instead of the smart mousetrap, we started working on the smart condo. And the smart condo is involving ambient sensors to observe the activities of people in a home non-intrusively, without cameras. The smart condo in Glenrose had cameras, but the patients did not like the cameras. Nobody wants to be filmed after a major surgery. You know, it's bad enough to be filmed now, that I had time to brush my hair, but really after major surgery, you don't want to be on camera. So that was a perfect application. And it all really changed the types of applications we were doing. We moved from the environment to health. And that was because of this collaboration of IBM wanting to try a cool new time series sensor data database Glenrose having a real suite that they were happy to instrument, and Lily Liu introducing myself and my colleague Jens Nikolaidis in sensor networks to the Glenrose. So this work led to at least 4 theses of Vlasenko, Vatanpour, Parisamohebi, and Shadan Kolestan later. So what did we do? Really, the high-level story is that we have 2 themes of activities. First, we started by saying, okay, we want to instrument a house with sensors. The sensors will be typically motion sensors and BLE, later, subsequently, Bluetooth low energy tags that can be recognized by smartphone applications. And we want to do that without using cameras. And we want to see how well can we understand people's activities. And what you see here in the video is our first student in the Smart Condo project, Julia Vlasenko. She's in the real video in the bottom image. And she's working in the kitchen of the Smart Condo. We have a real apartment on campus. Let me see, where is the Tin Man up on the top image? And you can see at the top, our Tin Man that's moving where Julia is moving with a slight delay. Now, the top video is really a video of Second Life, where we have built a model of the Smart Condo, and the Tin Man is simulating our inferences based on sensors. So the video that you see at the bottom screen of Julia is not being analyzed. It's simply used for evaluation purposes. And you can see that whatever Julia does, the Tin Man does a little bit later. And this is really the sort of easy to communicate demonstration that sensing with motion sensors and BLE only, when you have a single person in a home, can give you very accurate information about what the person is doing. And that was the objective of the original Smart Condo project, to go from sensors to models. So how we did that, the sensors are deployed. We did a lot of work on figuring out where to put the sensors and how to cover the space. That was the work of Julia Vlasenko. Then we took the sensor data stream and analyzed the various sensor events from the various, basically motion sensors. And we extract primary information about where the person is. And depending on where the person is, understanding what is there in the background. So if the person is really close to a bed and stays there for a long time, then the person is sleeping. So the inference about activities takes into account both location and the affordances of what is deployed in the space. And the visualization happens in a virtual world, Second Life. At the time, Second Life was very cool. And after we started using Second Life for simulating the Smart Condo, a whole lot of work happened with colleagues from business on understanding people's behaviors in Second Life and in the real world. I'm not going to talk about it, but the only reason I did this work, which is really very well cited even now, is because I knew how to program in Second Life, not me personally, my students. So then after we did that, we had a second phase that basically did the inverse. I will tell you a little bit about the Smart Condo contributions, but really working with the Smart Condo is terribly intensive. You have to put these things, they need batteries. We have to check the batteries all the time. You have to run experiments with people. These are very, very intensive. So we realized that in order to do smart homes work, you need a simulator. So we went the other way around. Now we built models of the space, of the sensors, and we integrated everything in order to produce simulations of what people do in spaces. So that's the high-level view, and that's really the Smart Condo project story. But let me tell you a little bit about what we ended up, more about the research that we worked on. So what we have deployed there is passive infrared sensors, and we put them on the ceiling. And when you project basically the coverage area, what you end up having is a diamond on the floor. And it is about 2 meters by 175. It's not completely square, but sort of close to square. And then we have eye beacons, which basically are attached to walls. And what they do is they cover a semicircle of 1 meter radius. So if a smartphone with an application is within this red area, the smartphone emits an event that basically says, I'm really close to that iBeacon location. So what events we have is every 3 seconds, we have, from every sensor, we have an event that says that this sensor fires, and this is from the passive infrared. And every 1 second, if the device is close to the semicircle, we get an event that basically says that this device, this cell phone, is close to this beacon, and this is the RSSI measure that indicates how close you are. As you can see here in the timeline at the bottom, iBeacons are truly bad. Basically, we have lots of outages. So having this data set, what do you do? So I want the idea is quite simple on how we do sensor fusion, but what I think is important here is the notion of what is the problem that we're solving. Before our work, everybody was trying to use, most everybody, all the work that we knew about was trying to understand people's locations from motion sensors. In fact, we participated in a challenge competition that we came in 3rd, I think, and the challenge itself was passive infrared motion sensors, find me locations. Now, if you're working with seniors, which is the case that we were interested in, you are told very early on that seniors cannot wear anything on themselves. So basically the idea that you have passive infrared sensors and you have multiple people in a home, that you're going to recognize everybody in the home, is just naive. The work was 1 person in a home, passive infrared works. That's what I demonstrated with the videos. If you have multiple people, it doesn't work. So what did people do when you have multiple people? Well, you give them all a cell phone. But the truth is that seniors will not wear the cell phone the way you want them to. They will not wear the pendants. They will forget. So none of these approaches work from a practical point of view. Excuse me. So the problem that we wanted to solve was, what if you have people who are having cell phones and 1 person who does not? So we have a target person who is not tracked, because that's the way it would work in reality. So that's the story that I want to tell here. The passive infrared sensors recognize that there is activity in 2 areas. That's the first block, A. So we know that there are 2 people someplace here. At second point in time, we have a beacon that recognizes a person. So in the second stage, we know that P1 is close to the beacon's location. So fusing these 2 pieces of information, we know that P1 is likely in the blue area, because the blue area is the overlap of the beacon and the 2 areas that are covered by motion sensors. So if you know where P1 is, through the process of logical elimination, you know where P2 is. So P2 is not being tracked, but it is understood, their behaviors are understood by understanding everybody else's behaviors. And so basically what we did to demonstrate that this works is an experiment. Now, how do you run an experiment in the real world? I know all of us have run experiments with subjects using our software. And it is a lot of work. You have to do the ethics, you have to sort of tell them what to do, but it's infinitely more complicated to run an experiment in the smart condo. So we recruited 26 participants, and we ran studies with 7 pairs. So the 2 pairs were working together in the room, and 12 individuals. And every experiment lasted 2 hours, and every participant was given a scripted activity protocol. So you can see our protocol here. These were very detailed instructions for what every participant had to do. And this was developed by our occupational therapy colleagues who have much more experience on human subjects experiments in the real world. So we had to tell them everything. You know, we gave them an app to give us information about what they're doing. And you have to give instructions that are very, very detailed, much like you would tell a young kid, put your personal belongings in the closet, read, put the glasses on. We have another work with wearable glasses, and instructions: sit on the toilet seat, take paper roll, flush toilet. Very specifically what they need to do, because otherwise we do not have the ground truth. So the ground truth specification is very exhaustive. And so we ended up with something like this, like a whole bunch of people went and they have these traces, and we have videos of them doing whatever we told them to do. And then what we did is we analyzed the videos. Parisa Mohebi did this exhausting work of actually looking at videos and annotating people's locations and activities at relevant timestamps. The way we did that is we had to put on the floor markers so that we have locations on the floor marked on the videos. And after all this work, what we found is basically, so Parisa was working on the combination of BLE sensors and passive infrareds before we had done work with multiple passive infrareds with one person and two people. And what she wanted to see is the relative information value of these two sensors. And what she found is that when you have single participant sessions and you use estimates, the BLE sensors, you get higher accuracy. Sorry, if you see here, the lower numbers are worse. Basically, you have higher error than the upper numbers, because the upper numbers use estimates. So estimates, when they work, they have a very small coverage area, 1 meter semicircle, where the other one is 2 by 2 pretty much. So if you know that the person is close to a beacon, you have a very accurate estimate of their location. So estimates are really useful. Now, if you look at two people sessions, when you have two people and when both of them are using phones and they are being tracked, you can see the difference. Does it make a difference if two people hold the phones or one person? It's pretty much the same. And this is only in the case of two people, because really, if you know the location of one person, then the person who's not been tracked is exactly there. But if you had more than 2, 3, then the situation would be different. So basically, if there's only one person that's not being tracked, then having a phone or not having a phone doesn't matter. And the last one was, if you only use estimates, because they're so much easier to stick on the walls as opposed to managing the passive infrareds, what you have is high quality, a dense deployment of estimates is pretty much the same quality as passive infrared. So that's what we learned from a technical point of view. And that was the work from sensor to models. And that work lasted up until 2017, I would think. And then we had a new student joining 2018, 2019, and that was Shadan Golestan. And he started the work on simulations. Because after the experiment with the 26 people in the smart condo took about a week, the analysis of the videos took an innumerable number of hours from Parisa, and I don't think that many students would have been able to do it as well. So at that point in time, we realized that there's no way we can work in the smart condo if every time we add sensors or we want to try a different configuration, we have to run such an experiment. So the game became, we need a simulation. So how do you make a simulation? Shadan developed this 3-component tool. The first one is we have to simulate humans. And I'll tell you how we did that. Essentially, we had to take the space model, the activity protocol, and make it into a way of simulating human activities. Once you have humans moving in the space, then you can simulate the behavior of sensors. So the same way we understood the sensor behavior to do sensor fusion, we kind of took the inverse to simulate sensor behavior. And then we had to figure out how good is the simulator. Like, do we trust this data? Do we know how it works? And looking at the literature, we found a lot of different approaches for how people measure quality of simulations. And essentially, we demonstrated that there are 2 useful metrics, in our opinion. So let me tell you a little bit about simulation of people, because this is becoming very interesting still and now continuously. So when we started with the virtual world modeling in Second Life, the model we had was just made up. Like, it was basically a 3D model in Second Life, much like it would have been in Unity. It does not have any logical description that this is the bedroom and this is the bathroom. But as we were working with a smart condo, we realized that we have to give information about, this is the space that has a bed, and the bed is, you can sleep in a bed. And here's a couch, and you can sleep on a couch. And here's a chair, you can sit on a chair. And here's a table and a side table, and you can put stuff there and eat. So these notions of affordances started being, additional information, a layer of logic on top of the virtual world model. And then somehow we figured out that there is something called building information models. And this is a work that is done in architecture and civil engineering. I see both of you nodding. So we discovered accidentally because we wanted to make up a model of the space. So now in our simulation, we have a BIM model of the space, not really a virtual world anymore. And we construct this based on industry foundation classes format. It's a typical format that has been exchanged. And what we have in addition to the model is something like the activity protocol, the daily objectives of a person. So these are the daily objectives of a person. A person has to eat during the day. Every time you eat, it takes about 30 minutes. Usually people eat 3 times a day. And in order to eat, you have to cook. And after you eat, you have to wash things. And the typical 3 times a day are between 8 and 9, 12 and 1, 6 and 7. So this is how people eat. This is the activity protocol of eating. So these are objectives. They're not exactly the protocol themselves. The protocol happens when you invoke a planner. So once you give these objectives to a planner, what you get is an activity trace. So at time 02, agent 1 is in that location and they are just there. And then they go to sleep sometime at 9.3. And then they walk and then they go and have some entertainment on TV and so on and so forth. So this is the activity trace that is produced when presented with set of objectives of an agent, basically an agent model, you would call it. So if you know what the activities are of the agent, now you can actually make a trace of what the agent is doing at any point in time. So here is a little bit of the mapping. So if you see at the activity trace at the top, there is a big gap between time 2 and time 9, because at time 2, the agent walking and they keep on walking around. And then the next thing we know is they go to sleep at time 9. But between 2 and 9, there is no information about their activity. So this gap is basically interpolated to create a trace. If the person is walking at time 2 and then is sleeping at time 9, then we just interpolate a bunch of events between these 2 timestamps to move the person from the original location to their sleep location. And this information comes from the model. So from the agent model, you get an activity protocol. And from the activity protocol and the space model, which is the BIM, you get a trace. So now we have a very detailed sequence of event, as detailed as we wanted, for what the agent does. And if you know what the agent does, then you can pass these events of agents, locations, and activities through a bunch of sensor models. Every sensor is simply a tuple that has a location and a coverage. A coverage is a shape on the floor, and we can deal with multiple shapes, but we have these 2 shapes as we had them from the real sensors. So you get the shapes from the sensor specification sheet. And now what you have is you have a component that at every timestamp knows where the various agents are and then compares the agent location with the sensor coverage areas and generates an event. And this event is either fired or not fired. So basically we have more information. In the real world, you only have fired events. In our simulation, we know at every point in time whether the sensor fires or is not firing. It kind of makes computation easier. So now you have exactly the same thing that you would have if you had real people moving around in the real space, or you have information equivalent. But how do we know that this is true? So we generated our simulations and we compared again back to the videos that we had from the experiments that I told you before, and we calculated 2 metrics. The first is we want to know if the sensors that we are simulating actually simulate their corresponding real world sensors. So we want to see if the order of the sensor events, not exactly the timestamp, if the order is the same. So if you have an agent simulating a real person in the real world, the simulated sensors would fire in the same sequence as the real world sensors. And that's the first metric. The second one is actually looking at the timing, because the timing is important in recognizing people's activities. So the first one is an easy metric. to optimize, easier than the second one. So we really want to have timings really close. And our simulator is, it is competitive. It's competitive with the state of the art. I don't have real gory details to show you. But basically, I think what is important is, for the most part, I think the world was using this metric. And we really wanted to add the temporal sensor readings to basically compare the timing in order to understand. Basically, it's a more accurate metric. So that's the work on the smart con. Oops. I do not know why this happened. Let me fix it so that I can read it. So as I'm fixing my slides, I would be happy to answer any questions. Hopefully there will be some questions.
Yeah, actually, I have one.
Please.
No, two actually. For the first metric, you say the order of the sensing is similar.
Yeah.
But that assumes that the activities that occur in the real world and in the plan are similar also.
Right.
Okay.
Very good point. So the way we did the comparison is, I showed you in the simulator, we give the task planner and it makes an activity trace.
Yeah.
We did not use the task planner for activity trace. What we did is we took the activity trace from the video. So the activities that Parisa had marked and said at this point in time, you are there. And then we interpolated to make the traces. So we did not use the planner to make that. So we knew that our activity traces were good.
Right.
Close enough.
Okay.
Yeah, very good point.
And for the temporal sensor reading, I'm assuming that, like, if I know that at time t0, the person is at this place, and 15 minutes later they are sleeping, I can assume that they didn't cross the space in like 2 microseconds, and they.
Yes.
So you have to have some constraints that say how fast they move, stuff like that.
Yeah, that is correct. So we have some, basically we have some body parameters. So bodies have to have some size, and this is how we calculate whether this body is within the coverage area. So it's not a dot, it's a cylinder that's moving around. And also the cylinder is moving with some speed. Now in our experiments, none of the people that were actually in the videos were seniors. They were all, young adult students. So the speed is, whatever, we calculated some speed from the motions and we just guesstimated. So these are the body parameters of our agent simulation. They can change, but I don't really remember the true values, and we do not play with the values. But you're absolutely right. We make some assumptions about the speed of motion, and that was one of the things that we wanted to play with, see whether different people, whether it makes a difference really to have accurate body parameters. But we never did that study.
Interesting.
So what did we learn from here? So the first one, we started with geometry model of the space. Like Julia Vlasenko started with architectural diagrams, and then they became images, and then we worked with pixels. And then with Parisa, we had arrived to Second Life and corresponding open source OpenSim tool. So again, we had 3D models that were quite accurate, but they were really geometry. They didn't have any notion of stuff. They knew about artifacts, but they did not have a logical description of the space. So eventually this led us to BIM, but we built all these simulators, kind of mapping the real world of, you have humans, you have devices, and we have spaces. And we got to experiment with virtual worlds of different types. The video that I sent you showed you is from Second Life. Now we're working with Unity, and we have a whole, I'll talk about that, the new toolkit that works with real BIM models in Unity. The thing that I learned personally much more intensely was how to develop experiments with human subjects. So there was so much more detail in developing the protocols. Before that, when I had people come into the lab to test our tools, We just gave them an introduction and we told them, do this. And there were a bunch of questions presented on the screen and they would do something and we have screen capture. So doing experiments with the tool is kind of very easy. It is time intensive, but it's very easy because you have screen captures, you have key loggers, you have a very good description of what's going on. It's easy to implement. But when you have a space and real humans moving around and doing things, the work is ridiculously more intensive. So we started experimenting with tools for video annotation, and that led to a few side projects. So that was the smart conductivity. There were at least 5 theses from my lab and another 3-4 people from the occupational therapy that were working there. We got an award for team teaching because the group was teaching a course that was kind of mixing software and occupational therapy. So it gave a lot of activities around this space. And it all happened because of basically the perfect accident of IBM software, a colleague, Glenrose, and the availability of this simulation space on campus. And this pretty much changed my subsequent career. There's like a whole lot of work came out of the smart condo. It's still going on now under the heading of smart buildings. So the second accident was due to AgeWell. AgeWell is a network of centers of excellence, and it started around 2015. So at the time, I had a student who was interested in model-driven engineering. Hafed, you remember, I had started working with models after UML, and even 96, the work that we presented to your conference was about the model-driven methodology for producing mobile applications of a type that was reading sensors. So modeling and code generation has been part of my thinking for a long time. And Victor Guana was the student who was working on model-driven engineering, and he was interested in domain-specific languages. And then in the context of AgeWell, we found an opportunity to use games for cognitive assessment as an example for Victor to complete his thesis evaluation. So the work was pure software engineering. We were looking for an example. Okay, we'll do games because AgeWell can use games. And I'll tell you a little bit about Victor's work. So Victor's work was thinking about basically this problem. You have a domain-specific language that describes your problem. So you define your model of the application, and then this domain-specific language specification is processed through a bunch of meta models. And the meta models basically look at your specification and pick up the concepts and add to them relations. And you may have many meta models that examine the language specification to describe different aspects of your application. And then these meta models can produce different, sequent pipelines of meta models. But eventually what happens is you take these meta models that you have and you plop code templates. So you take code templates and you instantiate these templates with information from the models to produce real code that runs. So this is the story. And in fact, Eclipse has a whole foundation, and it has multiple plugins to support this kind of development. And there is a language called ATL transformation language, which allows you to describe these models and transformation rules. And what Victor was saying that, okay, he wanted to see, how do you figure out if somebody goes to the code and changes something? Can you take the code and see why it is buggy? Can you trace the segment of code that may have been changed? Because nothing ever gets produced totally through this transformation. Somebody needs to do modification at the end. So if you go and modify a piece of code, can you figure out what elements in the meta models may need to be transformed in order to make it work? So basically his story was traceability. And what he did is this tool. So when you look for experiments, he built Chain Tracker, and I'll show you a little bit about what Chain Tracker does. But when you explain Chain Tracker, you go to the ATL page and you find a bunch of examples of DSLs and meta models and transformations and code. And the examples are very simple. So this example, I think, is coming from ATL Zoo. And basically it says that you have a bank model and a report meta model. So in the bank, about the bank has customers, the customer has credit cards, and every credit card has a list of transactions. And in the report meta model, you just need to find basically get all the people that belong in an institution, which is a bank. And what you have here, this is the UML model of the source and target. And then you have two. Okay, this tells me that I'm running late, but that's okay. So we have two sides here, the model-to-model transformation. These are a bunch of rules that basically explain how you map the bank meta model to the report meta model. And I just want to say that you have main rules and helpers that basically are mini functions that allow you to do operations on attributes of the meta model to produce attributes. The rules are pretty simple, basically saying the bank is mapped to a report and the institution of the report is the same value as the name of the bank, and the entries collection of the institution is the same thing as the customer collections of the bank. So these rules are explicitly mapping elements of the meta models, and these rules kind of transform elements and attributes to plop from the source to the target. And on the right, you have a code template, which is basically an HTML page that will be produced in when this report gets implemented. And what you see here is in the heading 2, there is a report institution. So that's a slot that refers to the target meta model report. So the institution of the report will go in this H2 slot. So this is the way you do model-driven engineering with ATL on the left and Axely on the right. So what does Chain Tracker do? Basically, it is a user interface that keeps track of implicit and explicit bindings. So the red lines, so here I will show you just the visualizations because it's really difficult to talk about the algorithm. I'll give you an introduction about what it does. The key contribution was it keeps track of explicit mappings and implicit mappings. And the implicit mappings are the mappings hidden in the helper functions. So the red lines are the implicit mappings that collect the customer report. If you see, let me go back here. So if you want to find the customer, how much money the customer has spent in total, they have to get the collection of all the balances of all the credit cards of the customer. So there is a helper here that relates the total spent amount of the customer with all the balances of all the cards. So this dependency is not as direct as the dependency between the name of the person and the name of the customer, but basically it has intermediate steps. So the latter, the helper functions, introduce implicit dependencies captured in the red lines here. And what you have is this parallel coordinate system that maps the source to the target meta model, from the target to the code template, and eventually from the code template to the final HTML page that gets produced. So what you can see here is basically, you can click on all the little edges and see correspondences at the bottom between the meta models and to the right to the rules. Several views. So basically here is a high-level view that connects with the ATL files, basically describes the ATL file that maps the report to the bank. Then you can see here branches. This is where I started. You can filter different things. So here the top is every dependency, but if you want to focus only on the person's, I'm not sure, this is not the name. This is the balance. The person's balance depends on the customer cards and the credit card balances. So these are two implicit dependencies from the total spend amount of the person in the target and the customer cards and the card balances on the source meta model. So you can do the filtering, you can annotate with information if you want to make notes to yourself on this model. And then you can see in the final step from the bank to the code template, you can see the mappings for what elements of the bank meta model map to what areas of the code template. And finally, you can see, oh, sorry, I think I made a mistake. What is this?
This is the visualization of ATL rules.
Correct.
Right?
Correct. So I was talking, so what I said is about the next slide. So these are the rules from one meta model to the code template here. And it basically indicates that the single bindings, you can choose a single binding, you can choose all the downstream bindings of an element. It's basically user interface show or off. And this is the last step of actually understanding what the elements of the template depend on. So, okay, so he had that and he demonstrated with these simple projects, but he wanted to do a big experiment, a good experiment, a real world experiment. So he came up with the idea he's going to write a game engine. So what do you do with a game engine and what games do you make? So suddenly we realized that he had this games engine and our colleagues in rehabilitation medicine, which was basically again Lily Liu from the Smart Condo, wanted to have these kinds of devices. So there is a test called star cancellation test. They give you a piece of paper and the star cancellation, the original one is the one on the bottom. And you have to find the stars. And based on how many stars you find and when you find them, the small, the big, the left and the right, they figure out what's your visual perception working. But occupational therapists have found that this is both boring, and if you do it with children, it doesn't work. The fact that it uses Western alphabets makes it more difficult for immigrants. And they were thinking that it wouldn't be nice if we actually made different variations of this. So here's a variation. If you have a kid, you can tell them to find the suns instead of finding the M's. If you have somebody who's Chinese, maybe you have Chinese characters. So we build a whole lot of different types of star cancellation tests on paper. And then we realized, okay, that's what 5DSL is good for. We're going to make them automatically because the only thing you need to change is really the screen layout. Everything else is the same. So he built 5DSL. Now the 5DSL is much more interesting than the bang experiment that I showed you. And he ran his experiment with comparing chain tracker, his tool, with Eclipse. So he ran two experiments. One is 5DSL and the other is a simpler one with ScreenFlow. And lo and behold, he found that chain tracker was actually useful in finding more dependencies, especially the more implicit ones, and especially in big cases. So ScreenFlow was an easier system. 5DSL was a more difficult system. So the chain tracker was much more useful in the 5DSL condition than it was in ScreenFlow. So we did not care about games. We did not care about ScreenFlow or anything about the tests, but we were looking for something more difficult. And our colleagues gave us an opportunity to do something. And that was good because Victor finished his thesis and he wrote a paper and he was able to say that, look, these are big and everything in the ATL zoo is small. The experiments were much smaller in other cases. But really, this work actually did not go further. Like Victor's work, I did not continue in it. But the games, the idea of 5DSL for games gave a whole industry of games development that was fun beyond the star cancellation test. So once our colleagues showed that we can make star cancellations, they said, okay, let's do something else. Instead of star cancellation, let's do whack-a-moles. So people have to see moles instead of finding stars. So we built a whack-a-mole, we built multiple whack-a-moles, and we tried them in case of delirium in hospitals. We tried them in day homes for people with dementia, and they were both enjoyable and useful. And then we built a whole lot of other games, so Bejeweled, Mahjong, working with a Chinese association, word search, and that's the whack-a-mole story. I'm not going to show them to you because...
Bejeweled.
Okay, so what happened in that story? The true software engineering line of work did not continue. Victor's work was good, but I haven't followed it up, and neither has he. But this accident of games taught us a whole lot about user interaction design because nothing worked actually with our seniors. You know, the colors were bad, they couldn't see them. The fingers were too big and they couldn't pass them precisely. So actually hitting the stars, only one star, and figuring out what they hit was just such a difficult job. So the implementation of placing and recognizing what has been hit changed about 3 times. The layout, how close they have to be to the center because things in the periphery were not found, how to give feedback, how to give sound, how to use the devices with a stylus instead of figure. All of the stuff I had never thought about. And I think they're relevant in many of the tools that we're building for software engineers, not as much probably because the constraints of people with limitations due to age are not necessarily applicable to the young software developers that we typically work with. But I have a huge respect for software engineering involving true user interaction work. And this work, this accident of, okay, we're looking for example, Victor was looking for example, I was looking for funding for Victor, AgeWorld gave us the opportunity. And this accident gave me a whole lot of work on building cognitive assessment games, which includes another project called Virtual Gym, which is eventually a spin-off. So that was what I consider the previous work in the Smart Condo is work that is truly software engineering and an application. This one, in this case, the true software engineering work kind of died off, but the applications took off in a way that was unprecedented and quite fun and gave me the opportunity to work with many bachelor students who are interested in doing these games and getting their feet wet with research in a cool environment. So that's the second story. And the third
that's cool. Can I?
Please.
I had a question before you came to, or you progressed to this last slide, the lessons learned, and you answered my question. So at the end, because there are a lot of research and publications around model-driven engineering and traceability, and it's yes, it's how can I say that, an issue depending on the domain. I'm specifically working at applying model-driven engineering in safety critical systems, and traceability is important. But I'm wondering how much the issue that was at the beginning to be solved was a real issue.
I agree.
Quantify that.
So, okay, we're recording this, but
yeah, okay. I'm sorry.
No. After so long, I was reading our papers again yesterday, trying to remember the gory details as I was preparing for this demo. And here's the original problem is valid. The problem is, how do you allow interventions outside this chain? And how do you keep track of these interventions while managing the chain of transformations? That was the problem. We never actually solved the problem. Okay. The work is basically focusing just on the chain and a good understanding of the chain. So the algorithm is kind of nice. So these implicit bindings can be quite complex. And if you just track the high level information, you do not have this explanation. Yeah. At the time, looking at the various traceability tools, I think our visualization is better. So there are matrix visualizations, there are some 3D visualizations. So we didn't compare against all possible visualizations, but I think there is a contribution in the implicit mappings and in the visualization. But we never solved the true problem of actually changing the transformations or doing manual edits. And I do not know anyone who, basically I have not been following this work after Victor graduated. He went to industry. He was not interested in pursuing, that's sometimes how the things work. So I think that the original problem that we started as a motivation with is valid. I think it's very, very difficult. And if the models are complex and if the risks are high, I do not know, I wouldn't trust our method to be terribly safe. Okay. So I would go with, testing more than with explanation and traceability. I would go with thorough testing as the solution to our motivating problem. Yeah. Okay.
Thanks.
I still like this area, but, this is a strange story. It's not, well, it's happy. The student graduated. He has a awesome paper. He has a bunch of papers. It was fun doing the games, but the true software engineering research is,
yeah, but it's really interesting. Interesting story. Thanks.
I know it was interesting for me to remember exactly how things happened. So now we're going back to sort of continuing after the smart condo. So in the smart condo, I had built this visualization, the simulation that I showed you, the video of Julia walking and the Tin Man moving with Julia. And that was actually compelling. You know, honestly, I thought it was a trick. It was just a cheap trick to demonstrate our work, because what I was interested in, oh my God, we understand this enough from the sensors. But people actually appreciated the video. And we have many videos since then, but this was the best video. Honestly, people like this video, it just was well done. And so people understood that our team knew something about spaces and homes and sensors. So Mohammed Al-Hussein is a colleague from civil engineering, and he knew about the smart condo. Of course, he did not know the details. He's interested in actually sizing the various, how to build walls, how to build 2x4s. So he has methods for planning how to size these things for a design. So he's working with BIM. And he knew that I was working with geometrical models of space. So he had a contact with CADSoft, which is a company that wanted to have a distributed software system where multiple people can propose edits to a BIM model. So they wanted, the scenario was, you have multiple people, you have me buying a house, and you have their decorator developing a kitchen design. And we're going to be doing things in parallel, maybe a husband and wife team on one side and the decorator on the other. That's what they wanted. So Mohammed came to me because I was a software engineer and I knew things about spaces. And then we learned truly about BIM. And this led to the work of Christoph Sidora. He got a master's, he was working on his PhD. Logan Gilmore built his own company out of his work. Faizan Navaz did some work on simulation, and Josh Van is working now on this. So we built a BIM kit, and I will not go into gory details. I'll simply say that we have a MongoDB repository that keeps track of all the elements in the BIM. Let me see, there is a question. Yes, thank you, Hafed. And then we have another element that has basically rules about what makes a good BIM model. So up to Christo's work, the rules were simply keeping track of the basic semantics. So you have to have 4 walls, and the walls have to touch the floor and the ceiling. These were the rules that people were talking about, just making sure that the IFC model is consistently exported. But the rules that we are interested in are rules about how do you place tables and chairs and couches in a space. They involve ergonomics, they involve aesthetics about balance and symmetry. So these are different rules that we're talking about. And if you have rules, then you can do model checking, or basically the original idea was we'll do model checking of a specific BIM model against the rules. But once we had the rules, we started doing generative design. You start with an empty space and you use the rules to place things. And if you have enough rules, you will find placements that are good enough and they are looking good too. And then the last thing that we did is, once you have a good model of the space, and we had a simulator built in the smart condo, well, you can do occupancy simulators, which is basically what everybody was doing during COVID. So that was a COVID accident. Part 3 is due to COVID. So because we have BIM, the first application we did, it was just augmented reality view of the BIM model. And what you see here, and these are videos, could show them to you, is basically somebody's walking the smart condo. This is the same smart condo that we had before, only it's renovated. We have fancy cabinetry as opposed to these ugly white ones that we started with. But what you have here is a BIM model that has all the furnishings on the tablet. And as Christoph Sidora is walking around, he can either find QR codes or landmarks like exit signs, and then he can synchronize his camera with the model element. So you can see this ugly brown, you can see the real brown cabinets and the reddish brown cabinets in the mid-BIM model. So you can see information about the space from the BIM model superimposed in the camera view. So that was kind of cute, but not really the true work. The true work of Christoph's master's was this model check in generative design. So he developed, again, domain-specific language for rules, and the rules involve properties of elements and relations between elements. So here, you know that every chair has to have, actually no, it's the other way around. It has to be less than 3 feet big. and that's a mistake. So basically he can check all the chairs and he can generate a report on what is good, what is bad about specific model. You give it a model. But the cool work about the generative was the generative design. So the way he did generative design for his master's is he starts with a BIM model, he superimposes a grid on the floor, and he's given a bunch of things that you want to place in the kitchen. So a kitchen must have a bunch of cabinets, a stove, a sink, a refrigerator. And there is a very important rule that the stove, the sink, and the refrigerator have to be in a triangle that's not too small and not too big. So they cannot be too close because the refrigerator and the stove kind of kill each other in terms of energy, but you cannot move around like crazy as you clean your stuff in the sink and you cook them or you take stuff from the refrigerator. So the ergonomics have some constraints about how big, how far away they have to be or how close they are allowed to be. And then basically his method realizes or relies on the fact that some elements are more constrained than others. So basically, if you want to think about it, the elements that have the more rules referencing them have to go first, because you cannot satisfy rules if you have placed everything else and you put something that has to depend on everything else that's already placed. So that was the key idea of how he does placement on the grid. And then he got some really good ideas. Basically, it's an exhaustive search. He places something, he makes sure that it fulfills the rules. In the beginning, the only rules that apply is the sink and the walls, and there are very few of them, they have to be attached. And then incrementally places more things, and he tries to optimize the evaluation of the rules. So the rules can be either logical, basically saying that the chair has to be at least less than 3 feet, that's the wrong arrow. And then if there is a rule that says that the chair has to be less than 3 feet, a chair that is 2 feet is better than a chair that is 2.9. So that's the way he evaluates the quality of a design, how close it is to breaking the rules. So that was his master's thesis, and then COVID happened, and then we integrated our human activity modeling and simulation with a BIM model, and that's a real model of the Athabasca Hall. And we tried 2 different ways of simulating humans. The one with scenarios, we basically made up stories about what faculty members and admin people and students do in a building, and we executed these scenarios. And then we made Markov models for when people come in and when they go out. And then we implemented person-to-person interactions as they move through the space as simulated wearable sensors to see how long people are close to each other. And if they're too close for a long time, then this is an opportunity for virus transmission. So what we did, the way we evaluated this work was by comparing to some data from an application we had built for the university that was simply counting how many people are in a space at any point in time. So during COVID, we had to declare that we are going to this building, to this room from 10 to 11. So this aggregate data was the only way that we could evaluate our simulations, and they were good enough. But the more interesting thing was that we were able to simulate different occupancy scenarios. I don't know if it happened in Quebec, but here we were considering ideas of having half the kids go to school Monday, Tuesday, keep the schools empty on Wednesday, clean them up, and then half the rest of the kids would go Thursday and Friday. Or half the schools will go in the morning, then clean the schools during lunchtime, and the rest will go in the afternoon. So we were trying to do these different scenarios and see how these different occupancy constraints would reduce the likelihood of virus transmission. And indeed, that was interesting. I do not know if it is correct or not, but I think it is an interesting experiment to think about what the implications of these scenarios would be. And, I thought it was interesting work, but it's not so thoroughly evaluatable, let's put it that way. But it led us to work with a whole bunch of colleagues who were interested in airflow, and we learned a whole lot about, okay, so that's a little bit of sideline. We had another student who was working on extracting BIM from images. So we had a particular relationship with a company, and he built an algorithm that basically makes a model of all the surfaces, the outdoor surfaces of a of a building from images based on the assumption that most elements of houses are defined in terms of lines. So he has a constraint solver that recognizes all these lines as edges in the image, and then he aligns all the views of the same line from multiple images to have an accurate model of the exterior of the building. And the reason he needs an accurate model is because they can build panels that they can attach outside for insulation of old buildings. And that's a company that was built. So that has something to do with BIM, but it's not the primary role, but it was possible because of the overall activity in our lab. That's why the company came to us. So we are working on smart buildings now, and we're instrumenting a new building on campus. And essentially what we learned, I mean, basically the more interesting contribution here is this notion of reasoning about BIM. We have a very good tool that understands the space. We have a whole lot of different languages for expressing rules and preferences and aesthetics. We're playing around with rules about colors and materials. And now the tool is good enough to be scalable to model buildings with 4 floors and a whole bunch of rooms, the building we're currently in, and we're stressing it out now. And soon we will have a real building that's heavily instrumented, and we'll be able to do true simulations and collect information from people on their experience. And that's the toolkit that I'm envisioning. And all of this happened, I think, in part because a colleague of mine had a need for a software engineer who knew something about spaces. That was the beginning. I mean, the rest of it is a whole lot of smart students, a whole lot of interesting answer stories, but the impetus came from somebody else's need. And I think for that I'm grateful. So in the end, what do I have to say? I mean, you have to conclude. So as far as I can tell, after 25 years at the University of Alberta, I think that if you're in software engineering, you can pretty much have license to work with anyone you want to work. So all domains use software, especially now. So you can think about what is the domain that you're interested in. I have colleagues working with music. I'm very keen on IoT. I love the notion of architecture. So that's how the smart condo evolved to smart buildings. Every researcher on campus can use software. So Lily wanted something to instrument the smart condo in the Glenrose. Mohammed wanted somebody to build a software system for collaborative development. All these opportunities come, and you can choose who you want to work with. I think for me, projects are both for what they're going to contribute as outputs, but to an equal degree is who I'm working with. A day is long, and you have to have trust in your partners, and you have to enjoy working with them, and you have to have an interesting, they have to be intellectually challenging you. You have to be useful to them. You have to be committed to this relationship when the research is not so productive. So when there are downs and the ups, when everyone is rosy, it's all good. But when things are down, you really have to like the people you're working with in order to pursue and get things done. And then industry. There's lots of opportunities to work with industry. So IBM has been a great partner to me, and we have had funding from them and from Alberta Innovates. But basically, you get all sorts of requests that may be, useful. And I'm not going to, reject any request without thoroughly considering it. But really, funding is fairly easier to find. So you have to be thoughtful about where you invest your students, not just for money, but also for the opportunities, the research opportunities down the road. Nobody can, I do not know that I have made the right decisions. I think that many of these decisions were lucky, but I don't think that they were pure luck. I think that there were, there were well-judged choices that could have gone either way, but they were more likely to work well. So check the opportunities, keep an eye for what is there, keep an open mind for what could be there, and enjoy the process. That's what I think the moral of these stories is, if I wanted to make a moral. So thank you for listening. Thank you for inviting me. I hope that was appropriate.
Very appropriate. I really liked your remarks and all the lessons learned. I have a question regarding the last project you talked about and all the opportunities it's open. It was Victor's work. I'm not sure. Regarding the tool in itself, to be able to lay out your, you have the walls and you have the furniture and a bunch of rules that constrain what you have. I was wondering, does that deal also with the evolution or the movement of the furniture or any changes to the model itself, the beam itself?
No, basically that's a very good question. We have been thinking about it because in the smart condo story, I told you that we have a model, and if the person is close to the bed, they're sleeping. If the person is close to the bed, to the chair, at the table, they're eating. Yeah. But chairs move. So I do not know if you're eating because the chair has moved. So we never solved that problem. In Christoph's work, Christoph Sidora is laying things out in the absence of humans. Actually, he's using a bit of, some of his rules refer to the human bodies moving in the space. So there is notion of what needs to be empty and how much walkability there has to be there. But we don't deal with changes in the space. Things are practically movable. But you're pointing a very, very difficult problem. How do you know where the bed truly is? Like if the bed is small, you can move it around. You can push the couch a little bit closer to the TV. So I wouldn't know if you move the couch, and I have a very light couch and I'm moving it around all the time.
Okay, yeah, that's great.
Smart condo wouldn't work in that situation.
Yeah, that's a big challenge, but yeah. Because what triggered my question is, as I'm in engineering school, I supervise undergrad projects. And lately, one of the undergrad projects I'm supervising with colleagues from the architecture department and other departments is about a robot that has to cover a space where we have sliding doors, sliding walls, and the furniture tends to. So the robot has its own sensors, but there is a beam model of the space. And that's a challenge for us for now. I just started on the project and I'm just getting to know the whole terminology and the beam world.
That is a beautiful problem, Ghislaine. I would love to talk to you more about it because our things are static, they have locations and shapes, but it would be gorgeous to think about their possible behaviors.
Yeah, so, exactly. And actually the robot is in a lab, but the final deployment would be in a hospital, where again, depending on the space, in an emergency space, they have the sliding doors, and so that's
so you can configure the space to contain things.
Yeah, because depending on how many people you have in an emergency, in the emergency, sometimes they just open everything, and everyone is sometimes because of pandemic situation or whatever, they have to isolate people, and they have doors, and so it's an interesting problem, and I saw. I'll go and look into the work.
I'll send you. I mean, Christoph has a nice paper in automation construction. I can send you his thesis, but the paper is much better than the thesis. Or whatever. It's better to start. And I would love to talk more about it.
Okay, thanks. Great. And thank you.
Very exciting.
Yeah, a lot of insights and interesting things to
Great.
to take into consideration by us researchers and students.
Perfect.
Hafid.
I have been nodding so hard throughout the presentation that my neck actually hurts.
Oh, apologies, but thank you.
So I was gonna say, I mean, it's scary to me listening to you, how much we think alike, except that you have been far more successful than I have been. So
You're just kind.
No, but I mean, really, I'm 100% in agreement with everything you said. Have fun doing whatever it is that you do. I like the idea of the accidents. In my case, it's too many research accidents, so I'm a little bit all over the place. So there is.
I find that's true for me too, and it is a challenge to tell the story to the Discovery Grant.
Yeah,
but
exactly.
We have to apply ourselves. Yeah.
My last grant. Some of the people who read it, actually, including Wissam here, said, you know, is this computer science? I'm like, well, you know, so. Also, you have no idea how timely this is for us right now, as a group. The whole stuff about the health applications, also about how to use the space, the detection, the simulation. We got the CFI grant last year, and one of our prospective projects, which we intend to do, is to actually study people, study this whole IoT thing, try to build an application that will be like a living lab, but that will be running permanently, and see how applications age, how people's perception of the knowing that they are being monitored, how that perception ages, face problems such as updates to the software, some pieces of equipment break down. What do you do? How that manifests itself in terms of software, architecture, etc. So this is extremely timely for us. And listening through your presentation, I realized how much we don't know, and how many of your papers we're going to have to read before we actually start. So again, I mean, that's why I have been nodding like crazy throughout all of your presentation. I will comment on another one. You said not all interesting work is easily evaluable. I totally agree with you. Yeah. Unfortunately, most of the interesting problems are not easily evaluable. And so as software engineering researchers, we're torn between what you can publish and what you care about. And sometimes or often it's not the same things. And so but I mean, if you will allow me to say this, I mean, you managed to do it well. I have similar mindset, but I don't do it as well. But you managed to do very well with.
You are just too kind. But I think what we are trying to do is pursue interesting things and find some slides that can be evaluated. Because I think you're absolutely right. The truly interesting problems are too complex to be solved and too difficult to say when they're solved. You're just kind of scraping a little bit and pushing a little bit. You're improving a little bit. And you want to have this sense to continue in the area, but you have to find smaller problems that are less interesting, but easier to describe and possible to describe in terms that can be assessed. And that's the process. And I think that's our responsibility as professors, because our students need to have this evaluation and this systematic understanding of research methodology. You have to have something that you can count. But you have to see it in the context of the bigger picture, or else everything that you do is a few small somethings that are well done and well specified, but they're not so terribly interesting, and they're not building towards a bigger picture. So that's the, you know, the balance that we are sort of trying to maintain. Sometimes we sort of succeed, but you're absolutely right in it is difficult, and it doesn't work all the time, right? Thanks.
Anyway,